I want to give the example of how to find the volume of a solid of revolution using the disks method. And this is not a thorough explanation, but I just want to give a quick brief explanation just to help our discussion. So if you have some sort of curve like this and you have a yellow region, and usually these type of questions would say something like this: you have a region bounded by some curves, and then you're going to spin this region around an axis. So for example, I might spin this around the x-axis, right? Then I'm revolving this region around and I get this conic shape. Okay, now to calculate the volume, what we're going to do is we're going to do a Riemann sum where we're going to take slices out of this. And so if I took that pink slice and I pulled it out and looked at it like this, it would make a perfect circle, right? Because I spun this region 360 degrees around that axis. So I have a bunch of circles stacked on top of each other. The center of this circle in this case would be the x-axis. And so I have a radius. And the radius is how far it takes to get from the axis up to the top of the curve. So the radius here is actually f of x at that point. Let's say this is the point x. Your radius is f of x. Okay, so if I'm trying to calculate the area of each one of these little slices, well, I just need to think about the area of the circle. And that's going to be pi r squared, or in this case, pi f of x quantity squared. So to calculate the volume of this whole solid, what I need to do is add up a bunch of these little disks together. So we can say it this way. We can say it's approximately the sum of going from 1 to n, a sub I, and then we throw in this delta x, because what we're actually doing is calculating the volume of each one of these slices, where this is not just a pure circle, it's a coin, right? It's a disk. It's got some sort of width to it, and that width is the delta x. Alright, now obviously the more of these coins we can fit in, the better the estimation would be, and what happens, it drives the width down, and so we get an exact volume by letting n go to infinity. And when we do that, that's a Riemann sum, we actually get the integral, and the integral comes from the formula for the area of a circle. It's pi radius, which is f of x, quantity squared, and then the width, which is dx. Okay, now I say all this because it's very common for a calculus student to try to just memorize this and then apply it to all the different contexts, but it doesn't give you the full understanding. You have to visualize here. This portion is the area of a circle, and in particular, the f of x here represents the radius of that circle, all right? And then the dx here stands for the width. And so we're actually taking the volume of a coin, adding up the volumes of all these different coins. Okay, so let's look at an example. Okay, so here I want to find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals 4 about the line y equals 4. Okay, and this is a very common question, these kind of things. Let's get a picture. If you're not getting a picture, you don't really understand what's going on. Please draw a picture. I don't know why you don't. Alright, so we're going to look at these two curves. That's our region. So we have y equals x squared, which is a parabola. It passes through the origin, and it's kind of our simple parabola. It looks like this, okay? And then it also says y equals 4. Y equals 4 is a horizontal line. So there it is. There's y equals 4. The region that I'm rotating around is this. And it says that it rotates around the line y equals 4. So that's different than what we showed in our previous example. We're rotating about the x-axis. We're actually rotating about this line here. So you can imagine if you took this shape and you flipped it upside down, and that's kind of your revolution. So you have this kind of lemon shape going on, and that's your solid. And we want to know the volume of that solid. Okay, and so this is what we're trying to take the volume of. Now, if you try to do a slice in the horizontal direction, it's not going to work very well, because you can notice that the top and the bottom are coming from the same function. And so that's going to make things kind of funny for us. So let's not do that. So what we're going to do is take vertical slices. In doing these, we can integrate with respect to y or respect to x, and it can be confusing sometimes knowing in which direction we're integrating. And what I tell my students is, look, notice if you're taking your slices, how are they stacking up? So these slices would be stacking up going along the x direction. That tells me I'm integrating with respect to x. Okay, so for my formula, I know that the volume here is going to be something to something pi, let's say r squared dx. And the reason I said r squared is because, remember, we're talking about a radius. And the reason it's pi r squared, again, remember, is because these slices are circles, and the radius is, well, we got to figure that out, but it's some sort of r value, okay? Now we also need to figure out what a and b are. We're going from what to what. And we can solve that question by figuring out what are these endpoints on my region here. Let's take my two curves and set them equal to each other. So I have x squared equals 4. Taking the square root of both sides, I get plus or minus 2. So this is minus 2 over here. This is plus 2. So now I'm integrating from negative 2 to 2 pi, and we just got to figure out what this radius is. So we can visualize it. I'm going from there down to there. That's my radius. And this is the line y equals 4. This is the curve y equals x squared. So my radius is actually 4 minus x squared. You can imagine if I took that circle and brought it down here, I'm trying to think of this radius. What is this radius? Well, we had 4 minus x squared. That's how we go from the top to this curve. Okay, so we have 4 minus x squared, quantity squared, and then we have our dx. And this is why I'm saying don't just memorize the integration formula for the disk method. You have to understand where you're getting these pieces from. Otherwise, it's going to be very difficult. So here I'm going to integrate. We can take out the pi, and I want to FOIL out the 4 minus x squared. So that gives me 16 minus 8x squared plus x to the fourth dx, and that's a polynomial. So that's pretty easy to integrate. We get pi, let's see, that's going to be 16x minus 8 thirds x cubed plus 1/5 x to the fifth, going from negative 2 to 2. Okay, now another thing I can notice here is that this shape is completely symmetrical about the y-axis. The left side and the right side are the same. So what I could do, instead of going from negative 2 to 2, is I could double this and just go from 0 to 2. And again, the reason that works is because I'm symmetrical about the y-axis here. Okay, so now from this point it's just arithmetic, and we need to tread lightly. So let's see what we get. We get 2 pi, 16 times 2 minus 8 over 3 times 2 cubed plus 1/5 times 2 to the fifth. Okay, all that minus 2 pi, plugging in 0 for all my x's. Well, they all zero out. From there, we should get 2 pi. Okay, and we just do some arithmetic here. So we got 32 minus 64 thirds plus 32 fifths. You can bring all that together. You should end up with 256 fifteenths. So we end up with 512 pi over 15, and that is my volume. Okay, now the integration part itself, the calculus part here, going from here to here, was pretty easy. That's not very hard. And the arithmetic down here can be tricky, okay, but if you're careful, you can get it right. The hard part was setting up my integral right there. Okay, and that's why you have to keep in mind, it's not just pi f of x quantity squared, it's pi times whatever my radius is. In this picture, which is a big mess of color by now, just remember that I started at y equals 4, and I'm going down to the curve y equals x squared. So the radius of each of my slices is 4 minus x squared. So we have pi 4 minus x squared, quantity squared, dx. I hope this makes sense. Solids of revolution can be tricky, but you got to know the parts. Try to engineer it. Don't just try to memorize. And I think you can do it if you work hard enough. If you have any questions similar to this one, I'd be glad to help. And thank you for watching.